Okay, one, I hope everybody is doing well, staying at home, sitting around, not being able to come to class. Um, and also, this is going to be a little bit informal if my clothes are not obvious. I'm aware this is not the best way to do this, and like I had said in the messages I've sent you through Blackboard, I'm trying to set up some type of Zoom meeting, or if that doesn't work, something else, just so that we can actually more or less meet face to face in a live setting where you can ask me questions. And for those of you who that won't work for, I'll try to find a way to either record the meeting and then post it to Blackboard so those who can't make it to the meetings will be able to watch it. Or if that doesn't work, for those who can come to the meeting, I'll kind of make another video like this going over all the questions from that meeting that we go through and then post that to Blackboard too, so you can all get as much information as possible. But as of right now, I'm assuming you're all done your exams, and now we can kind of go back to what we were doing before all of this started, where we were looking at different sequences and series. And in particular, now we've kind of gone past the sequences, and we're just looking at series and trying to determine when they converge and when they diverge. And as I said in class, we don't necessarily know why we're doing that or why it's important, but we get there eventually towards the end of the chapter. And I'll also point out this is the only whiteboard I have in my house, which is really big and all of that, but it's still not ideal. And obviously, there's not a lot of room for writing. So I would suggest, at least as far as like the theorems I write here and the definitions, they're in your book. Just pull those up and kind of jot them down in your notes so you can see them, just in case you have trouble reading this. You can also pause this video and write them down, but whatever. But I think last time we were talking about tests for convergence or divergence, and we said the only one we actually knew about at the time was the nth term test for divergence, which said if the sequence does not approach zero, then the series diverges. And we had pointed out in class when we looked at a few examples that the test can only show you divergence. There isn't any way to get convergence. So you just kind of have to keep that in mind. Ultimately, all of you are going to have to know all these different tests, and you're going to have to be able to write them out, write out the conditions for the test, and then draw the correct conclusion from the test. And so far, the only test we have is a test for divergence, which we said occasionally is inconclusive, and then we have to rely on a different test. And today we're going to start looking at one or two other tests we can use. And again, I kind of keep reiterating the same thing. A lot of the tests we do will have cases when they're inconclusive. And with practice, you begin to understand, oh, I should use test A, I should use test B, test C, or whatever. And that's kind of why we go through these and why I give you all the homework, so you can practice each of the different tests and get a feel for when you should use this test versus that test. But I think the series that we finished with the other day was the series, I think we called it the harmonic series, 1 over n. And if we looked at the sequence associated with that, which is clearly the sequence 1 over n, if you take the limit as n approaches infinity, that limit is equal to 0. The nth term test for divergence says if the limit is unequal to 0 it diverges. That one has a limit equal to 0, which does not mean convergence. It means, according to the test, inconclusive. So we have to do something else. And I'll also point out as I do this, I don't necessarily feel the need to make 37 of these videos over and over and over if I make a mistake. And that whiteboard is hanging by a tiny little nail. So if it just falls off in the middle of my lecture here, I'm not going to restart this. I'm just going to rehang it and keep on going. So bear with me and maybe it'll be funny if it falls. Okay, so at the end of the last chapter, we talked about improper integrals. Integrals like maybe the integral from 1 to infinity of 1 over x. You gotta remember we're talking about functions here. 1 over x dx, or the integral from 1 to infinity of 1 over x squared dx. And when we did those improper integrals, we did the whole trick. I'm not going to go through all the math again, but rewrite this as a limit, integrate, plug in a value, say t for your limit, and then see what it approaches. And if it approaches a number, then the integral converges, and it converges to that number. If it diverges to infinity, then the integral diverges. There's no value because it goes off to infinity. And admittedly, those are continuous functions. And we do stress here that now we're talking about series, which are coming from sequences, which are definitely discrete. The series are just a sum of a bunch of discrete points. But we can kind of think about it, and here is where I want to keep the theorem written there. We haven't gotten to it yet, but I can kind of draw right here, and you'll forgive me, you know I like to draw in as many colors as possible, but I wanted to make sure this was clear, so all my markers are black, so it's as dark as possible. But suppose we have, say, 1 over x squared. We know what the graph looks like. It looks like that. And we'll start it right at 1 because that's normally where I take my integrals. And we said as far as it went, I'm not going to scribble on here, but if I want to find that area, I do the whole improper integral limit trick, and I end up getting that it's convergent. Because basically we said it gets small enough, fast enough, that most of this area is irrelevant, and so then it will converge. But we can actually kind of think about a trick here. We're talking about sequences and series, adding individual discrete points up. But hey, for right here, suppose I looked at the series 1 over n going from 1 to infinity. Now, I know if I look at the sequence of partial sums, I'm just adding up a bunch of fractions. And I can kind of label them here. This is 1 over 1, which is 1. Maybe this point is 1/2. Maybe this point is 1/3. This point is 1/4, and so on. And now what I can actually do if I want, to find the sum of this series, I essentially want to add up all those points. And one trick I can use is to add up something bigger. So maybe I can add up, maybe using Riemann sums and rectangles, I can add up that rectangle right there. And I can add up this rectangle right here. And I can add up that rectangle right there, and so on and so forth. And clearly, if I can add up these rectangles, well, the rectangles are bigger than the actual discrete value of this point right here. Because the discrete point is just one value, the rectangle is a whole area. So whatever that area of those rectangles is, if I add it up, it has to be bigger than the sum of that series. But I know if I want to find the area of these rectangles, well, that's a Riemann sum. I can just integrate. So I can just integrate the integral 1 over x squared dx, which is clearly, sorry, this is 1 over n squared, because I'm using 1 over x squared here when I graphed it, so we're going to use 1 over n squared here. That's one of the things I'm not going to erase this whole video and start again for. But it means clearly the sum of this series is less than the sum of those rectangles. But the sum of those rectangles, I'm not going to do the integral out. We've already done it in chapter 6. I'm sorry, that's my trig class. In like chapter 3. And we know that that converges. I don't really care about the value. But since I know it converges, then this converges to a number. We'll just call it k. And the sum of this has to be less than that, which means this has to approach some number. For the sake of argument, I'm going to call it m, and that has to be a number, which means it has to converge. Which then tells me that apparently this series converges to a number. But I can kind of expand on that trick a little bit. Suppose now we'll look at the one we were looking at last time, and we'll look at the series 1 over n. Well, I can do the same thing. I can graph 1 over n, which I know looks like that, and I can plot those individual discrete points that I care about, 1, 1/2, 1/3, 1/4, and so on. And, well, now, instead of using right-hand endpoints like I did before, I'm going to use left-hand endpoints over here. And I'll get this area, and then I'll get this area, and and then I'll get this area, and so on and so forth. And now I know that if I want to add up the sum of these individual values here, well, now I can kind of do the same argument that I did before, but kind of use it in reverse. And now clearly, whatever this is will be bigger than the sum of those rectangles. But I know the sum of those rectangles is the integral from 1 over n, or 1 over x, I keep flipping my letters, from 1 to infinity. And I know that that integral right there actually approaches infinity. Which means that integral approaches infinity. This sum will be bigger than that integral, which means this sum has to be infinity. And to a certain extent, we can do this for a whole lot of our series, but we can actually shortcut it with this test right here, which just kind of gives us a nice way of working through this using what we already know. It's called the integral test, and it says, and again, you can look in your book if you want to see this written out, or just pause the video and write it down. Let f be a function that is positive valued and decreasing for x is greater than or equal to 1, and a sub n equals f of n. Doing exactly what we did before, taking a sequence, and writing the terms of the sequence as the values of a function for all n's. Then the infinite series a sub n converges if and only if the improper integral converges. Or put another way, if the series converges, it will only converge if the integral converges, and the series will only diverge if the integral diverges. So, bear with me, my cats are running around all over the place, so I'm trying to follow them. But anyway, what that means is, I can look at a series, I keep writing integral, we can look at a series, say the series from 1 to infinity 1 over n. If I want to use this test to determine if it converges or diverges, then I have to come up with a function that will agree with that for all n. So we'll just use f of x equals 1 over x, exact same trick we used in class before. Then I'll take the integral of 1 over x from 1 to infinity dx. I'm not going to integrate that out. You'll bear with me as I fix this because apparently my cat hit it and it slid sideways. Okay. Now I want to integrate that. If I integrate that, again, I'm not going to take the time to do it, but I know this integral will go to infinity. We did this before. Now, since the integral approaches infinity, that tells me the series approaches infinity and it diverges.